So again, here's our situation. We have an object traveling through space. It has clearly a momentum, and it is in space so that there's no external force acting on the system. Under those conditions, this object's momentum would remain constant for all time, for all points in the future. Even if I extend it to a larger system, I could have a system right now with another object of similar mass, but with a velocity straight up, even if it's the same velocity, straight upwards. These two objects together form a system. And in this system, there is a net momentum. Now, it's important for you to understand that that net momentum is likely in this direction, that this must be the momentum of the system. Because one object has momentum to the right, the other object has momentum to straight up. So there's a net momentum in that direction. Now, it is quite possible at some moment in the future, these two objects may come into contact. The way it's drawn, maybe not, but if this box had started a little bit sooner, they would come into contact. And it doesn't matter what the result of that collision is. If there's no external force, the direction of the momentum will stay in this direction, no matter what happens in this collision. The first box could rebound off of the second box, and we would still have a net momentum in this direction. Momentum is a conserved quantity, which means that if there is no external force acting in the system, the momentum of the system will stay the same. Now, I'm trying to emphasize external. Let's assume for a moment they don't interact, that there is never any contact between the two. But instead of it being in space, we change it and we place it on the Earth. So that one object has been fired horizontally and one object has been fired upwards. Under this condition, will the momentum of the system stay the same? Does this system conserve momentum? We have an external force now. Now, what makes something external to the system? That's been something I've been trying to impress upon you, and I think I've just created confusion. For a force to be external, it has to have certain qualities. For one, it has to act on both objects in the same way. And that seems easy, but it has to act on both objects in the same way. It doesn't have to be the same force or the same size, but it has to act on them in the same manner. That's an ambiguous term because I want to make sure it fits every situation. But the second thing, and this one is the most important, is that it has to act on both objects in the same direction. Now, I want to be very clear, very clear. I made that second condition up. But I made it up because it's an easy thing to see. And it's more likely to be the kinds of problems we will face. Both of these objects are going to experience a downwards force. One of them is clearly going to increase the velocity of the object, this one. Because its horizontal velocity will be unaffected. It's going to acquire vertical velocity. It's clearly going to increase the velocity of that object. Thus, its momentum will not stay the same. The other object, it's probably going to decrease the velocity for a while and then increase the velocity. This one clearly is not going to have the same momentum all the time. Thus, the gravitational force is going to change the momentum of the system. The system is not going to continue to have momentum in this direction. We can probably all imagine that that momentum is going to change direction after a while. Now, gravity's an easy one to see because it affects all the objects the same, but we could have wind blowing on both of these objects. It might affect the objects differently because we know that wind is air resistance and the wind currents don't have to be uniform. But clearly, if it's a windy day and the wind is kind of blowing through here in some kind of random, non-uniform way, that would be an external force on the system. Even though it might not be the exact same direction on everything, it has a general tendency to change the momentum due to something external to the system. So I would not expect it. I do want to be very clear, though, that an external force does change the kinetic energy of the system. It might not change the energy of the system, but it would change the kinetic energy of the system. Let's be careful. If it's a conservative force, it doesn't change the energy of the system. It converts the energy from one form to another. But every external force changes the kinetic energy of the system. Period. It must. It causes an acceleration, and acceleration is going to change the velocity, therefore the kinetic energy changes. We can only say that energy is conserved under those circumstances if it's a conservative force that acts in the system. Only then is our external force conservative and will conserve energy. All right, so let's get rid of gravity for a minute. Go back to having this be in space. And I want to talk about collisions. So that's really what today is supposed to be about, is dealing with collisions and angular momentum. There's clearly going to be a before and an after case here. There's going to be something that happens before. And if you want, we can have a during and then an after. Now, truthfully, I don't really know what's going to happen in the long run. I don't really know what the outcome is going to be. I know that likely after the collision, there will still be two boxes. That's likely. I don't think there's a chance that the box that's not moving is going to be going to the left after this collision. You guys pretty good with that? Is it probably terribly likely that the box will have some kind of velocity to the right? I'm not trying to trick you. It'd be hard after this collision for the box on the right to suddenly pass through the box on the left and be moving to the left, right? That seems unlikely. We kind of know how physics works a little bit. But the first box, I don't really know what it's going to do. I know it's going to probably have less velocity to the right. And the reason I know that those things have to be true is merely because the physicalness of this situation. If we consider the boxes again during, and this is where I would really pay attention. Well, you should always be paying attention, but let's consider during for just a minute. There's the point of contact. This is when there's an interaction. This is where an impulse is exerted. All the vocabulary words we've tried to work into our program here. Interaction occurs only through force. And we have a variety of forces that can be involved in an interaction. But during an interaction, the forces involved must be a Newton's third law pair. That's what makes it an interaction. In this case, it's very likely the force involved is a normal force. And the first box is going to experience a normal force to the left. This is due to the contact. That's going to reduce the velocity of the first box. That's why I know the first box is going to be either going slower, it's going to stop, or it's going to be going backwards afterwards. Those are the only possible outcomes. It's not going to be moving faster to the right. It can't. The direction of the force dictates what happens to its velocity. In the same way that the box on the right is going to experience an equal and opposite force to the right. The only options for its motion after the collision is for it to have some velocity to the right. Now, how much of each of those things happens depends on the interaction, on things that I can't easily decipher. There's just too many variables. I don't know how soft the surfaces are, which will determine how long the two objects are in contact. I don't know how much the surfaces influence each other during this normal force. I just don't have enough information. I can tell you, though, after the collision, the momentum is going to be mv. It has to be. No matter what, mv was the momentum before the collision. So mv has to be the momentum after the collision. You tend to forget that. You tend to think that I have to shape my momentum in terms of what is happening now. And that's not true. In this case, the forces that acted were internal to the system. They formed a Newton's third law pair. The only forces that occurred were an interactive force between two objects. Because of that, I know the momentum had to stay the same for the system. But I also know that each of the two objects changed their momentum. I could write that the momentum after the collision is actually mv1 plus mv2. That's fine. But I don't have to know what v1 and v2 are. And there's no reason to believe I do know what they are. Which is why knowing that momentum is conserved doesn't necessarily tell you that you know what happens during a collision. All the things we just talked about, all the forces that are acting, all the changes that occur, still don't tell us what v1 and v2 are after the collision. For that, we would need more information. We would need to know more about the collision or more about the results of the collision. Like them sticking together. That's a significant issue. They stick together, they have to have the same velocity. So v1 would have to equal v2. So they add things to the problem to make the problem something we can solve. But to the physics, the momentum after the collision had to be the momentum of just the first box. And be aware, this problem is very, very straightforward. The truth is, any interaction that involves a Newton's third law force still conserves momentum. The Earth and the Moon have a complicated dance, but the system conserves momentum because the force between them is a Newton's third law force. It's due to gravity. In that case, the force of gravity on the Earth is equal and opposite to the force of gravity on the Moon. That forms an interaction, and because it's an interaction, it conserves momentum. It could be said that these two boxes probably experience gravity. And if they experience gravity, that would be an internal force. But it still wouldn't change the momentum of the system. It might change individual momentums of objects, but not the system. Now, so we're going to start with far fewer things. But instead of our second object being small enough where its shape didn't influence the problem, we're now going to look at having our second object have enough extension, enough size, where the interaction is going to be influenced by the size of the object. And I think this is a good example of that. I think you guys can probably think, critically about what would be the result of this interaction. Let's assume that we are looking top down on this, that this is two objects that are on a frictionless surface like ice. What do you think the result of this collision is likely to produce in the two objects? So let's talk about the box for a minute first. What do you think the result of the box striking this rod will be? All right, so I think we can say that. We can probably say it slows down. I think that's all right. That's probably the easiest to suggest, that it will have a new velocity that is slower than before. All right, the rod. What's likely to happen to the rod? So, the rod will gain velocity, but let's be clear about it. Is the rod going to move in a strictly linear way after this collision? No, it is likely that after the collision, the rod will now have some kind of rotational speed. But it's also likely to have some linear speed as well. Now, before we go into this too much, there's probably something that you guys don't know that I've talked about it, but I've only talked about it in a relatively passing way. And I really need to make sure that we kind of nail it today. That if you throw something, just throw it and give it a spin, it doesn't just spin about some random point. Unless an object is given a fixed axis of rotation, objects will spin about their center of mass, period. I want you to try this weekend. Try and throw a Frisbee, but instead of throwing it the way you would normally do it, do the little flick with your thumb. You guys know what I'm talking about? A lot of people try and throw it with their thumb, like flicking it backwards. I'm saying that because if you're holding it by the edge, then you are creating an axis of rotation about the edge of the disc. If you let it go, it doesn't stay rotating about the edge of the disc any longer. The moment you let it go, it immediately begins rotating about its center. It won't stay rotating about its edge. This is true for anything. I would not recommend doing this unless you have a big enough place to do so, but grab a bat and just throw it. That's why I said I don't recommend doing this. But if you do so, the moment you let it go, like the instant while it's still in your hand and you're just about to open your hand, the axis of rotation is either about the handle or your shoulder. Like if you just have it in your hand, just kind of flick it like that, the axis of rotation will be right there at the end of the bat where your hand is. And if you do it from your shoulder and throw it, then the axis of rotation will be where your shoulder is. But when you let it go, it will spin about its center of mass only. It won't stay spinning about your shoulder. You understand why, right? That it's going to spin in such a way that there's equal mass on both sides. Because if there isn't, it would wobble and torque until it did. So all objects naturally spin about their center of mass. If you fix an object in place, it can have a different axis. So if this object is resting on the ice and there's a collision, then there must be a rotation about the center of the object. Now, here's the hard part of this discussion, the part that students have difficulty identifying. The rod now has angular momentum and linear momentum. And we know the linear momentum of the system because the linear momentum of the system is mv. Has to be the linear momentum of the system. There's no way it can't be because that was the momentum of the system before the collision. If you want to take this problem and look at that instant of the collision like we did before, take a look at the during part of this collision. There's the during part. And during the collision, the box experiences a force here. While during that same moment, the rod is experiencing a force and a torque. Now, the problem is in saying that the rod experiences a torque and the box doesn't. The box must also be experiencing a torque. because that is occurring due to the exact same force. The problem is that, how do we measure this torque on the box? The box doesn't rotate after this. The rod does. I mean, it's clear, it's easy to see that if the center of mass is here, there's going to be a torque arm length there. How do we quantify this idea that the rod now suddenly has angular momentum? And there was or appeared to be no angular momentum in the system beforehand. And we don't rectify this, not the way that you think we're going to. Instead of rectifying it by saying that the box somehow created angular momentum that wasn't there, we say that the box had angular momentum before the collision. Now, this doesn't make a lot of sense to students the first time they see it or the first time they understand it. Well, I'm sorry, if you understand it, then it does make sense. Students tend to have difficulty the first time this is presented to them. That somehow, how does the box have angular momentum before this collision? It wasn't rotating. And the answer is less interesting than it sounds. Look, if it was just the box by itself, and the rod never existed there, then we would never say that the box had angular momentum. We wouldn't. It doesn't make sense. It's not rotating about anything. However, in a bigger view of what's happening here, we can say that the result of this collision is to create angular momentum in the rod. So in a bigger view of this problem, we recognize that the box must have some angular momentum as compared to the box rod system. Meaning, we don't talk about the box having angular momentum on its own. We talk about the box interacting with the rod in such a way as to impart momentum and angular momentum during the conditions where there will be angular momentum after the collision. That's how this is discussed. So when we talk about the angular momentum of the box, we try to be very clear that the box only has angular momentum with respect to what's going to happen between the box and the rod. Remember, we're trying to find a way to make predictions about what happens in our environment. So the rules that we're using here are designed by humans to suggest how we can observe the universe and make sense of what's going to happen. So I want to use a specific example now. I want to get down to more of the nuts and bolts of this. I'm not going to change this very much. I'm going to continue to deal with a box of mass m and velocity v. But to make this a little more rooted in things we know about, I'm going to table this discussion till another time when we can actually get through all of this and feel like we know some things. All right.